All right, so we're going to start with topic 5, energy. So it is review book pages 82 to 98. And like I said, that's not a lot of pages in the chapter. So you should definitely read it over, if not outline it. Now, when I say outline, you can write it into on a separate sheet of paper, or you can highlight the key stuff, but I'm not collecting that. It's just a suggestion, a very big suggestion. All right, so let's go into some review stuff. The first thing is, what is energy? Okay, and again, we're on pages 82 to 84. All right, energy itself is the ability to do work. All right, this morning, I was a crabby person. Why? Because it's Tuesday, number one, after a break. And that's always worse than coming back on a Monday or even Wednesday. Number two, I hadn't eaten yet, which means that I didn't have energy stored up. So not only did I not sleep, but I hadn't gotten my energy from eating. Two major components for a human being to actually be able to do work and have energy. Okay. So energy itself exists in a variety of different forms. You guys have dealt with 2 of them already. Do you remember what they are? Anybody remember what the 2 forms that we have dealt with in this class already?
Oxygen.
That's not a type of energy. That's an element. Do you remember what types of energy?
Matter and antimatter?
No, those aren't really types of energy.
Potential,
kinetic. Oh wait,
kinetic, potential, mechanical,
renewable energy.
Renewable, exactly. So it's a variety of different ways that energy will actually exist in. One of them, not only do we have kinetic, potential, mechanical, renewable, all those fun things, right? We have electromagnetic. Okay. Now, electromagnetic will interact with the environment in 4 different ways. Okay. We have reflection, transmission or refraction, scattering, and absorption. And I will give you guys a second to copy that down, and then we'll get into more details about that. I'm just trying to find you guys on here in case I get to the point I want to, and I want to join on my iPad so you guys can see stuff. Okay. So reflection is exactly what it sounds like. It reflects off of something else. It bounces off of something else. Okay. Transmission and refraction is more like when you put a straw into water. Can you guys see that? How you can see the straw is here, right? But then when you look at in the water, it looks like it moves, but it really didn't. It's just the way that the light has. You guys can see that, right?
Yeah.
Okay. It's just the way that the light is actually refracting throughout the water, okay, and will make it look like it bent, but it really didn't, okay? Then you have scattering. Scattering is exactly what it sounds like. You go to, well, not right now because of COVID, but on a normal situation, you go to a friend's house for pizza and soda. And all of a sudden, the parental units come home and doesn't know that you guys are coming over for pizza and soda. What do?
Hide.
Hide. What else do you do?
Run out.
You run out. Now, Anna, you said run out, right?
Yes.
That's okay. Are you, Kasmira, Jared, and Hannah going to pick the exact same route to run?
No.
I don't know.
Probably not. It's you guys are like when you turn on the light and cockroaches scatter. Okay, that's like you guys when you are at someone's house and you're not supposed to be. Okay, you scatter in every direction. The same thing happens with electromagnetic energy. Okay, when it scatters, it goes in every direction. It doesn't just go in one direction. Okay, it's the same kind of a thing. And then we have absorption. Absorption means to take in. Okay, so we have reflection, refraction, scattering, and absorption. 4 different ways that it's going to interact with our environment. Okay, I want you guys to highlight this. This comes up all the time. Okay? The properties that are going to affect absorption or radiation. Okay? The two properties are color and texture. Okay? If you have a black t-shirt on versus a white t-shirt on, which one is going to absorb more? The black?
Black.
Right. The black or a darker color is going to absorb more electromagnetic energy, okay, versus a white colored t-shirt, okay? It's why most of the time, some people are crazy, but usually if you're going to go sitting outside on a sunny day in the middle of summer where it's 102 degrees, you're not wearing your black sweatsuit. I mean, you wouldn't wear a white sweatsuit either, but black sweatsuit would be a bad idea unless you really wanted to sweat, okay? Because black is going to absorb that electromagnetic energy more than, since at 110, okay, more than something that is white that will reflect it, okay? So darker colors absorb, lighter colors reflect. That's also why, if you think about it, okay, with texture, a rough surface. Are there a lot of you guys who are in music?
I am.
I know, Jared, you are.
Me.
Jeremy. So there's a decent number of you. How many of you guys have been downstairs in the music rooms in those soundproof rooms before?
I have.
Me.
Okay, what are the walls made up of?
I have no idea.
Styrofoam?
It looks like styrofoam, right? Probably not styrofoam. It's more of a foam type thing, not a hard foam. But it kind of looks like if you took an egg carton and you put it up against the wall, but it was soft, right? So it's got those dips. Yes, no, maybe?
Yeah.
Yeah.
Talking about. And what color is that?
Gray.
Right.
Black.
Dark color, right? There's a reason for it. The reason it is soundproof, I mean, some sound does come out, but it's soundproof enough is because those walls that are a darker color and a rough texture, that's because it's not like completely smooth, right? It's got some shape to it, right? Are going to absorb that sound. It's also why, guys, before Christmas, right, we had that snow day. In other words, it was a day that just had snow, right? When you went outside for the first time and the sun was shining on the snow, a lot of times you get blinded, right? Because it's snow ends up landing and it's very smooth and it's that bright white, which means that any sunlight that hits it gets reflected into your eyes. Okay, so if things are darker colored and rough, they're going to absorb more. If they are lighter colors and smooth, they're going to reflect more. You need to make sure you understand that. That shows up from now until the end of the year and into next year. Okay? All right, so let's talk about kinetic and potential. Now, we already went over it, where kinetic is the energy of motion, right? And potential is the energy that's absorbed. Okay, we know kinetic energy gets used during motion, potential energy, like right now, right? When you guys have lunch, which is probably, if you didn't have it already, you probably have it next period, okay? When you have lunch, you're sitting down, and a lot of times if you're about to eat, you're like, I'm so tired. Why? Because you don't have enough stored energy. When you are using your brain, you're actually using energy as well. That's why, guys, when you get to college, or some of you guys are doing it now, which is still a little weird, you should not be pulling all-nighters at all because it's really bad for you. But if you are studying really late, all of a sudden you start getting hungry, but you don't want a salad. You want like a bucket of chicken wings or a pizza. Why? Because your body is craving stuff that will give you instant energy. Okay? It needs more energy. You need to absorb more energy before you can start studying again. Because yes, you do burn calories by studying, believe it or not. Okay? Next, you have transformation. Now, transformation is when you start off in one type of energy and it transfers into another one, right? So you notice at the top of this picture here, right? You see how like clean the waterfall looks, and then all of a sudden it gets more misty, right, as it goes down. That's because of the fact that as it's moving, right, we're changing the type of energy that was there. So as it was slowly moving here, right, it was more of a potential energy type of situation, but then the faster it moved, the more kinetic energy gets used, and that's also why it turns into more of a mist. Right. So we talked about temperature being the average kinetic energy earlier this year. All right. Now we're going to talk about thermal energy and heat, because they are not the same thing as temperature. And if you're not sure, if you look at your screen, I kind of made that obvious, right? Thermal energy or heat is not the same thing as temperature. Temperature is a number, okay? Heat is not. Heat or energy is not. Or it's not just a number. Okay? So heat is the total amount of energy, whereas temperature is the average kinetic energy. Okay? Everything on the left is going to be heat. Everything on the right is going to be temperature. Okay? For heat, our units are joules, okay, or a capital J. That's going to be our base unit. Now, you can have kilojoules. You can have millijoules. You don't really use that so much. But joules is going to be our base unit. Whereas for temperature, we deal with in science more of the degrees Celsius and Kelvin. Yes, degrees Fahrenheit does exist, but not to anybody else outside the United States. So, or it's U.S. territory. So we really deal with degrees Celsius and Kelvin. That's the units for temperature. The units for heat are going to be joules. Okay? With heat, you're talking about the energy value. Temperature, you're dealing with how hot or cold something is. I'll give you guys a second. Let me know when you guys are done.
For like the first one, total energy is for temperature?
Heat.
Oh, heat.
Everything on the left of the verses is heat. Everything on the right of the verses is temperature.
I finished.
Anybody still good? Anybody still need it?
I'm good.
Okay. This should look familiar because not only did we do this already, but this is on your reference table. So for this class, you don't need to memorize how to go from degrees Celsius to Kelvin or Kelvin to degrees Celsius or Fahrenheit to Kelvin or any which way. Because if I said to you, you have 80 degrees Fahrenheit, which is right here, you can just look and say, oh, okay, this is 80 degrees, which these all go by twos, right? For Celsius and Kelvin, it goes by 1. So if it's 80 degrees Fahrenheit, I look over, that's approximately 26.5, right, degrees Celsius, which leads over to about 299 Kelvin, right? It also, you're lucky on here, even though I made you guys memorize it, the temperature that water freezes in all three of them is here, which means that's also the temperature that water melts at, because the freezing point and the melting point temperature are the same, right? This should all be review for you, right? And the temperature water is boiling at is also listed here, right? And it's also the condensation point temperature. Okay, do you guys remember that? I know it was from a long time ago. You guys remember?
No.
You don't remember. Okay. Okay. Well, good news is it's here for you. All right. So we use these. We've already done this. Fahrenheit, Celsius, and Kelvin. Right? We did this already. Yes?
Yeah.
Okay. Just making sure. Right. Did this. Okay. So what's happening inside of a beaker or a round bottom flask, as this is? Round bottom flasks do not stand up on their own, guys, just so you know. So this would have fallen over by now, and whatever liquid that is would have spilled everywhere. So because it's got a round bottom, you know, it just doesn't stay. All right, so here the little red dots in here are representing the molecules that are inside of the liquid. When you heat something up, right, your average kinetic energy is going to increase, right? Because you're heating it up, you're adding energy to it, right? Which makes the molecules move faster. When the molecules move faster, they're more likely to bump into each other, but also bump into the thermometer. That's what makes the little alcohol strip that's inside that red part of the thermometer go up. I know a lot of you guys have not used these thermometers at home, but they are the best ones. A lot of you guys have the digital ones now, which are not as good. But look, so as we add heat, the molecules move. Okay, so every time that one of those molecules hits into the thermometer, its extra energy gets transferred to the thermometer, which makes the molecules inside the alcohol part of it move faster and rise up. Okay, this is all about energy transfer. You guys with me so far?
They're still copying.
What? Who question?
Yeah. So like transfer energy is like there's such thing as a transfer energy, right?
Transfer of energy.
Oh.
It's like if I have a stylus here and you say, Ms. G, I need a stylus for the day. And I go, here you go. I no longer have the stylus, but I transferred it to you. See what I'm saying? That's what it means.
Yeah, so like the molecules are transferring energy to the thermometer?
Yes. So what's happening is if I heat up the round bottom flask, if I heat it up and I am adding energy to the molecules move faster and are going to hit into that thermometer. Every time that they bump into that thermometer, they transfer that extra energy to the alcohol in the thermometer, making it rise up. Because now the molecules inside of the alcohol are moving faster and want to move away from each other more. Because remember, the more energy you have, the more you want to move away from everybody else. That's why gases are so much further away from all of the molecules versus when you have a liquid or a solid. Do you remember those when I did particle diagrams? Did I do particle diagrams with you guys? Where they were like super close together in a solid, a little bit further away in a liquid, and then super psycho in gas?
I don't remember that, but I remember it in bio last week.
Okay, so I'll do it again with you guys, right? So here we have air molecules, right? In the cold air molecules, right, you're going to have less energy, right? So versus the hot air molecules, this has to be an open container in order for the molecules to escape, right? Versus in an open container, right, we're adding heat to it, which makes them move away from each other as far as possible. Right? So this what would happen. Okay? That's important. Right? Why? Because as I'm heating up the molecules, right, I am adding energy to the molecules themselves. Right? And they're going to want to move more. That kinetic energy is making them move more. So what ends up happening is if it's not a closed container, hot air is going to rise up. Okay? So what happens is you add heat, your kinetic energy increases, which makes your density decrease. Okay? You guys learned things that are less dense go to the top, right? You guys remember that? So that's why hot air is going to rise. And during the summer, the last place you want to be is in your attic. Because in your attic, it's going to be the highest point, usually where there is no air conditioning. And some houses, like my mom's house, has a house fan that during the summer, we would turn on the house fan and it would release all of that hot air out of the house and actually naturally cool down the whole house because all of that hot air rose up to the attic, and by letting it out, it kept it away from all of us. Kind of cool. Okay, yeah. All right, so let's talk about specific heat. All right, you guys need your reference tables. On page 1 in the top right-hand corner, there's a thing called specific heat. Okay, and we're also on review book page 89. Now, for those of you who are planning on going to chem, okay, I'm going to give you more information than you just need to know for earth science. So you're going to want to save these slides. Okay, you need them for earth science right now, but I'm going to get into more details with this. All right, so specific heat is the amount of heat energy needed to raise the temperature of a substance that is 1 grams by 1 degree. Okay, so it's the amount of heat energy that is needed to raise the temperature of 1 gram of a substance by 1 degree. Now, it does not matter if we increase it by 1 degree Celsius or 1 Kelvin, because it's a 1-to-1 ratio. If I raise the temperature in 10 degrees Celsius, I'm also raising the temperature by 10 Kelvin. Okay, that's why it only says by 1 degree and it doesn't specify units here. Everything in the universe has its own specific heat. They're all different. Okay. This formula here, okay, is the formula that you're going to need to know. It's called Q equals MC delta T. It's a heat formula. Show this all the way down. Okay. All right. Where Q stands for heat, M is the mass, right? C is what's known as the specific heat capacity. All right, so I'll help you guys out. So if it's Q equals MC delta T. Oh, no, that should be capital T. Okay. Q is heat value. Okay. So that's going to be in joules or kilojoules. M is your mass, which should be in grams. C is your specific heat capacity. Okay. Right. And if you look, that's going to be in your, if you look on your reference table, it's in joules per grams degrees Celsius. Okay. Now it can be joules per gram Kelvin as well. Okay. And
thought it was times degrees Celsius.
nope, it is times degrees Celsius, yes, but you can write it like that. So it's joules over grams times degrees Celsius. It's just so that the units will cancel. Okay. Anytime you see the delta symbol, it's going to mean change, which you should know from math. Okay. It's going to be delta and then some other letter. Whenever you deal with this, it's always going to be the final value minus the initial value. So in this case, we're dealing with our change in temperature. So it's going to be whatever our final temperature is minus the initial temperature. Okay? The delta T can be a negative number. You didn't do anything wrong. The difference between a negative and a positive is just that you released the energy instead of gaining the energy. That's all it means, is that you release the energy versus gaining it. So if you get a negative value, it means that the energy was being released. Negative in this case is not necessarily a bad thing. You guys good so far?
Yeah, I'm good.
Thank you, Brandon. Okay.
What's the initial value?
It depends on what it is. So in this case, it's going to be the initial value of the initial temperature, because it's delta T and T stands for temperature. So in this case, we're going to talk about the initial temperature versus the final temperature. I'm just giving you a little bit of background information. Okay. Here we have the reference table that is on page 1. Okay. Notice that all of the material that is here has a different specific heat value, which makes sense because everything has a different specific heat value. Okay. For liquid water, what this 4.18 means is that if I want to take my water, if I take 1 gram of liquid water and I want to raise the temperature by 1 degree, I need to put in 4.18 joules of heat. Okay. To make it a little bit easier for you guys, another value or another unit that can be used instead of joules is calories, right? If you want to get into shape, some of you guys have done this before, okay? You just can't get obsessive over it. But if you wanted to get into shape, right, you need to know how many calories you intake per day so that you can go run it off on the treadmill in order to lose the weight, whatever it is, right? So it's how many joules of energy do I need to output in order to burn off those calories. It's the same thing here, okay? Lead has 0.13 as its specific heat. That's a very low number. That means for every 0.13 joules of heat energy I put into a sample of lead, the temperature of that piece of lead will increase by 1 degree. Okay? Versus liquid water, you need 4.18 joules of energy to raise it by 1 degree. And notice that it is different. So for liquid water, it's going to take a really long time to boil or to get hotter versus lead because it is so low. All right? If we are talking about a phase change, you are only changing the potential energy. That's when you have something melt, you're increasing it. Anytime you go from a solid to a liquid to a gas, you're going to increase the potential energy. Okay, so if you go from a solid to a liquid to a gas, you increase the potential energy. If you go from a gas to a liquid to a solid, you decrease the potential energy. And that should make sense because in order for something to melt or vaporize, you have to put heat energy into it, right? In order for you to boil your water to make your mac and cheese for dinner, right, you have to add heat to it. However, if you're boiling the water and you go, oh crap, Miss G has extra help right now, and you turn off the heat before you run away from it, but you turn off that boiling water, by the time you come back, is that water still boiling?
No.
No. It will happen spontaneously, but its potential energy is now going to decrease because now you're going from a gas to a liquid. Okay, so anytime that you have a phase change, so when you go from a solid to a liquid to a solid, a liquid to a gas, or a gas to a liquid, or in terms of sublimation or deposition, when I skip the liquid phase altogether and I go from a solid to a gas, or a gas to a solid in cases of deposition, okay, your potential energy is going to change, and it's going to be the only thing that changes. You guys good?
Almost
still
have one
happening.
more.
Okay. Just so you know, solidification and crystallization is just a fancy way of saying freezing.
Okay.
Okay. So we are going to draw in our notes, okay, what's known as a potential energy diagram. Okay, we're going to draw a potential energy diagram. Okay, and this is specifically going to be when we're heating. Okay, this is what's known as a PV diagram. Okay. And guys, on that note, I believe the class period is over. Make sure you get this before you go. I will be posting homework for you in your review book. Do I want to do that? No, I won't. We'll start here tomorrow. Okay?
Okay.
Once you guys drop,
Bye.
I will talk to you
Bye.
tomorrow. Be good.
Bye.
Bye, Ms. Gonzalez.
Bye. Be good.